Hello and welcome to Sciencing. I'm a Sciencing. Today we're going to be talking about vacuum. But first we need to understand the numbers a little bit better. So we'll talk about exponentials. We use exponentials or powers to represent very small and very large numbers easily. Today we're going to start with the base of 10. So if I take 10 to the power of 1, or 10 with an exponent of 1, that's the same as saying 10, because you've got a 1 here and a single 10 here. So now if I go 10 to the power of 2, that's 10 times by 10. That's the same as saying 100. So next, if I go 10 to the power of 3, that's the same as saying 10 times 10 times 10, which is 1,000. So you can see I've got a 3 here and 3 zeros here. So now if I want 10 to the power of 6, that's the same as saying 1,000,000. But what if I go the other way? So 10 to the power of 0 gives me 10 divided by 10. That equals 1. You can see from this, anything to the power of 0 is 1. Next, we go 10 to the power of minus 1, and that's 10 divided by 10 divided by 10, which is 0.1. And then 10 to the power of minus 2 is 10 divided by 10 divided by 10 divided by 10. That gives you 0.01. That's all well and good, but let's say you want a bit more accuracy than this. What you can do, let's say you want to say 6 million, you can take the number 6, times it by 10 to the power of 6, and that is 6 million. Or if you want even more precision, you can go 6.5 times 10 to the power of 6, and that is 6.5 million. So, what is vacuum? No, not that kind of vacuum. Well, one definition is that it's a space without any matter. However, we can't achieve that. It's impossible, but we do our best. What can we achieve? The LHC runs around 10 to the minus 10 to 10 to the minus 11 millibar. But what does that really mean? 1 bar of pressure is what we have on Earth in atmosphere, which equates to roughly 2.5 times 10 to the 19 particles per centimetre cubed. This is a centimetre cubed. And we're saying that there's roughly 10 million times more than 1 trillion particles in 1 centimetre cubed. And a millibar, which is the unit I said earlier, is 1,000 times smaller than that. And in the LHC they use a number even smaller than that, so it's 10 to the minus 10 or 10 to the minus 11 millibar. So that's roughly 2.5 times 10 to the 6, so 2.5 million or 250,000 particles per centimetre squared. And to put that into another perspective, space is roughly 10 to the minus 12 millibar, so only an order of magnitude less than that. So, why do we want vacuum in an accelerator? Well, we're trying to get our small bunch of charged particles to go as fast as possible with as much energy as possible. And gas particles are quite large and slow. So if our particles hit them, they'll slow down or knock them off course. The way I imagine it is it's like somebody on a bicycle trying to go as fast as possible. Then you've got lots of large trucks going in random directions that will knock them off course. So how do we create this type of vacuum? No, not with that. That would only get you down to about 800 millibar. To create this type of vacuum, we usually need at least 2 different pumps, because gases flow in different regimes. The 2 different flow regimes we're talking about today are going to be viscous flow and molecular flow. Viscous flow is what we see in atmosphere, where the particles of gas act together as a group. This type of flow is in pressures above 10 to the minus 1 millibar. Molecular flow is when the particles act independently, like baubles on a table. They don't interact with each other because there's so much distance between them. This is usually at pressures below 10 to the minus 3 millibar. The technical definition of molecular flow is when the mean free path is larger than the size of the container. This means that there's so much space between the particles they're more likely to hit the container than each other. So the next question is, how do we get down to these pressures? Well, first we've got to get out of viscous flow. To do that, we use pumps known as roughing pumps. They give you a rough vacuum. These work on a similar principle to vacuum cleaners. Yeah, you can come back now for a little bit. They suck air out of the chamber. I'll leave a link in the description below if you want to read more about these. In molecular flow, that's where things get a little bit more interesting. There are two different types of pumps for molecular flow. There is active pumping and passive pumping. Active pumping pulls the gas particles out of the system, and passive pumping usually traps the particles as they make contact with the pump. We're going to be doing a small experiment now, something you can do at home. It's not related to accelerators, but it is related to vacuum. What is the fastest way to empty a bottle? Well, here I have my bottle, here I have my timer, and we're going to try a few different methods. The first one, we're just going to turn the bottle upside down. You can see it's quite a slow process. Next, we're going to pour it, as you might do normally. You can see that was probably a little bit slower. Maybe if we turn it upside down and shake it. No, that was really slow and quite messy. And now for the secret fourth option. I've seen that before, but I wasn't sure which one would actually be quicker, so I thought I'd do a test. And as you can see, this one is the fastest method. The reason behind this is when you turn the bottle upside down, the water initially escapes and creates a weak vacuum behind it. At some point, the force of the air outside the bottle needs to restore the pressure, and so the water stops flowing while the air gets back into the bottle. The reason spinning the bottle and making a tornado or whirlpool is the fastest method is because the water can leave the bottle and air can replace the empty volume at the same time. So now we've heard the explanation of why it's faster to empty a bottle like that. Can we have a more practical application? Yes. Here I have a glass and a carton of juice. It's a full carton, so when I tip it, I'll get the same glugging effect you saw earlier. However, there is a way to avoid this. If I take a very sharp knife and I stab the back of the carton, like so, I get air able to come back in, and so it pours very smoothly. An example of an active pump is a turbomolecular pump. These have two sets of blades. One is stationary and the other is spinning. The spinning blades have to move at a similar speed to the particles they're pumping, so they usually spin around 1,000 times a second. They have to move this fast so they can give momentum to the particles that they're pumping, so that the particles are more likely to get pushed out of the system rather than bounce back into the system. Trapping pumps can either chemically or physically trap the gas particles that make contact with them. One example is a neg, a non-evaporable getter. These are very reactive to most of the particles that make up the gas. And if the gas particle hits the surface, they are very likely to react and stay stuck on the surface rather than bounce back into the chamber. So with all these ways to get particles out of a system, why can't we get a perfect vacuum? Well, this is because of a phenomenon we call outgassing. Everything you can put in a vacuum chamber outgasses, because there are always particles on the surface or inside the porous structure that are physically or chemically attached that can escape. One of the worst chemicals for this is this stuff, dihydrogen monoxide. There have been many deaths due to inhalation of this substance, and it's been known to corrode and oxidize many metals. It's also known as water. Why is water so bad? Well, at room temperature and atmosphere it's a liquid, with lots of particles at different energies inside. So I realised while I was editing I should explain this. When you measure the temperature of something, you're measuring the average energy of the thing. So some particles inside will have more and some will have less energy, and the distribution usually looks something like this. So you can see when something's cold, it still has some particles with high energy. When something is warm, it has more particles with high energy. Because there's this pressure from 10 million trillion particles per cubic centimetre above it, most of the particles can't escape. As you reduce the pressure from the surface, particles with higher energy can escape, leaving behind the colder particles. And this keeps going until the water freezes. But the frozen water still outgasses and will spoil your vacuum. How do we reduce this effect? Well, we use active pumps to get as low a pressure as possible, and then we heat up the system for a few days to give as many of the colder particles enough energy to escape. As we cool down, less of the particles are stuck to the surface, and so we get less outgassing and a better vacuum. I hope you've enjoyed the video, and I hope I haven't outgassed too much. If you've got any questions, as usual, leave them in the comments below, and don't forget to like and subscribe. Bye! Was that video too long? Did you find it too boring? Did you have trouble concentrating? Well, fear not. Here's a quick summary. Number 1, vacuum is nothing. Number 2, you want vacuum in an accelerator because you want nothing to be in the way of your really fast particles. Number 3, water is really bad in an accelerator because it ruins your vacuum because it outgasses so much. Number 4, water is really good for your body because it helps you concentrate and keeps your body functioning well. So, I'm going to introduce you to my friend, the whiteboard, which I just hit myself in the face with. Ow.